Alright, so in this video we're going to look at a couple quick things around equilibrium. So write the Kc expression for the following reaction. 2 SO2 gas plus O2 gas goes to 2 SO3 gas. And then we're also going to have to write the Kc expression for the reverse reaction and take a quick look at the relationship of that. So quite simply a Kc, right, is simply going to be looking at the concentration, so the molarity of, in this case, products over reactants. So SO3 squared, okay, so that coefficient 2 means that it's squared. It's 2SO3, so it's SO3 times SO3 or SO3 squared over SO2 concentration again, and there's two of them, so squared times concentration of O2. So if you knew the concentration of SO3, SO2, and O2 at equilibrium, you could plug them in right there and get the numerical value of Kc. Now the Kc expression for the reverse reaction. Well, looking at the reverse reaction, it's simply going to be 2 SO3 gas goes reversibly to 2 SO2 gas plus O2 gas. Now the Kc for this one, again, we're going to do products of reactants, so it's going to be SO2 squared times O2 all over the concentration of SO3 squared. And therefore we can call that K prime C. Okay, I mean it's the Kc of this changed reaction. Therefore Kc is equal to the inverse of K prime C, or vice versa. K prime C is equal to the inverse of Kc. Okay, so with delta G and delta H and delta S, if you flipped a reaction around, you would take the negative of it because those are products minus reactants. Because this is products over reactants, when you flip a reaction around, you take the inverse of the Kc, or the Kp if you're dealing with all gases and using that measure. Alright, so in this case, we are given a Kc, or you could be given the information in order to calculate it, the concentrations of each one at equilibrium. But in this case, we're given the Kc, and we want to know if it's 7.9 times 10 to the 4th at 800 Kelvin, what's the value of the Kp expression for the reaction below? So we're going to convert from a Kp to a Kc. Okay, there's a couple ways we could do it. We could go and plug in that the pressure is equal to molarity times R times T for each of the substances. If we knew the concentration of SO2 and O2 and SO3, we could plug all those in. Kp is simply SO3 squared times divided by the pressure of SO2 squared times pressure of O2. You could calculate it that way. But in this case, we're just given the Kc. We want to find the Kp. We need to use the following equation, that Kp equals Kc times RT raised to the delta N, change in moles. And that delta N equals moles of gas and the product minus moles of gas and the reactants. Okay, so when we go through and look at this, quite simply we're going to say Kp is equal to our Kc, 7.9 times 10 to the 4th, times this quantity R, 0.08206 from Earth's liter atmospheres per mole Kelvin, therefore temperature needs to be Kelvin, which it is, times 800 Kelvin raised to the -1 because it's 2 in the product, and it's 1 and 2, 3 in the reactants. So that's that. The reason for this is simply if you plugged in each one pressure, instead of Kp, you put in pressure equals molarity times R times T. You would have it squared on the top because it would be inserted there, and it would be cubed total on the bottom. So RT squared over RT cubed is RT to the -1. So we simply plug that through, and we get that the Kp is equal to 1,203, or with sig figs, it's 1.2 times 10 to the 3rd. All right.